Hello everyone, welcome to the series of voltage gain calculation for the common source amplifier. So in this video, I have taken the example. In last video, I explained the concept of voltage gain calculation. So here the structure is input is applied. Okay, yes, input is applied here and the output is taken here. If we carefully look at the M2, it is a PMOS amplifier. So it is a PMOS transistor where the input is at gate and output at the drain. So it is the common source. First of all, we have to identify the topology. So first thing is to identify the topology. The topology is common source because the output is taken from the drain. Now, now we have to look at the impedance or can say effective impedance at drain. Now the second step is to look at the effective impedance at drain. Because if we are calculating the output at drain, means we have to calculate the effective impedance at drain. So this is the second step. And after that, third step is simply to apply the common. So the third step is simply apply small signal. Third step is apply small. So yeah, first thing we identified is a common source amplifier. Second is the effective impedance at drain. So if we are looking from the side of drain, then we can say this: if we are looking to calculate the effective impedance at this point, then we have to look at upper side, then we have to look at the bottom side, both the side, because for the DC analysis, sorry, AC analysis, this is going to be 0. So means this side, this M2 in AC in AC analysis, this M2 is going to provide the impedance, which is nothing but a parallel to the impedance of M1. So first of all, I have to calculate the impedance of M1. So now impedance of M1 from its drain. So this thing I explained in the last video. You can see it. So this VB is nothing but DC voltage. Is a bias voltage. We are doing the biasing for this M1. So this is going to be 0. Now, this is your drain. So we have to compute the effective impedance at drain. That I am saying it is at Rout 1. So for this structure I explained in previous video, this R out is nothing but this R out is R naught. So this is the output impedance of transistor 1. Now we have to calculate the impedance for this. So for AC analysis, this drain is 0. Oh, sorry, source is at 0. And for output impedance calculation, we also make the input 0. Actually, small input is small signal, but for output impedance calculation, we make all the source to be 0. So this V in is also 0. So this R out is to nothing but for the PMOS. I didn't explain about the PMOS, but you can see if we are looking from the drain side, this is drain side here, and this is drain side of PMOS. If we are looking from the drain side and the source and the gate is 0, then its impedance nothing but R out 1. And similarly, here will also R out 2. So we can see that if it is a PMOS or it's an NMOS, if we are looking from the drain, its output impedance is nothing but an effective impedance when we're looking from drain. So now we can see that. Now again come at this amplifier. Now this drain has the effective impedance, which is nothing but, and this thing is your input is applied, and here this thing is 0. So this is similar, which is the common source with the PMOS. This is a common source with PMOS. If we draw this small signal or if we do the intuitive analysis for this topology, we know that gain. So this R out is nothing but an effective impedance when we are looking from the side of output. So this is minus GM. What is the GM? This GM is for M2 because your main input is output is minimum main input is applied across the M2, or we are calculating the gain from V out to V in for this M2 only. So it is nothing but a GM2. So I will write here GM2, and this R out is effectively R out 1 parallel to R out 2. So it is nothing but R naught 1 parallel with R naught 2. So this is the complete expression for the gain. Here only lambda is not equal to 0 means CLM is considered. But if we consider the body effect, here body effect will not come into the picture because for this your it is connected to ground, body is at lower potential, and here the body is connected to the higher potential, which is VDD. So body effect is not going to come into the picture because for AC analysis this is going to be 0. So source and body at the same potential, and this body is already at 0. So this source and body at the same potential. So we have to carefully look at these steps. First of all, we have to identify the topology, which is a common source in this case. Second, we have to calculate the impedance at drain, or can say effective impedance from the side of output. And after that, apply the small signal on M2. Here, I didn't draw the small signal, but this thing I explained in the previous videos. So you can see it from there. So you can draw the small signal, or you can do the intuitive analysis for this. But directly, I can say this is a minus GM2 R naught. R out. This R out is effective impedance, which is R naught 1 parallel to R naught 2. So now come to the second question. Yeah, this is the second question. So this question is almost similar at the previous one, but yeah, in previous one it was M1 was NMOS, but here this M1 is nothing but a PMOS. Okay, so they made it zero. Initially it was like BV, bias voltage applied here. So yeah, for AC analysis it is zero. So it is looking like this. So the first step is topology. So input is applied at gate, output is taken at drain of the PMOS M2. So this thing is first step is it is a common source. Second step is calculate the effective impedance. Calculate the effective impedance from the output. So effective impedance, and it is simple topology, so no need to apply the small signal. So second step is important, effective impedance and output. So at output, we can see again, if you are looking downward, this M1 is here. If you are looking upside, this M2 is here. So for the M1, this is your PMOS type, and this source is gate is connected to ground, drain is connected to ground. So this source, now we are looking from the side of source. So this is R out one, and we are looking down from the side of source. So this thing I explained for the NMOS, if we are looking from the side of source, your effective impedance is nothing but 1 upon GM, GM1 plus 1 upon if lambda is not equal to 0. If lambda is not equal to 0, means this R out 1 is equal to 1 upon lambda 1 ID. Okay. So this is the simple method of calculating these things I explained in previous video. So this is the calculation of R out 1. And now we have to calculate the R out 2. So R out 2 is nothing but when we are looking from this. So yeah, this source is at zero potential and the input is 0. Is when we are looking from this drain, it is your R out. So you can see this topology is very simple. Your source is grounded, your gate is grounded. You are calculating from the drain is a PMOS, whether it is a PMOS or NMOS, don't worry. So it is going to be R out. So the effective impedance, when we are looking from this output, the effective impedance is at output is R out 1 parallel with R out 2. So it is going to be 1 upon GM1, if I am not considering CLM for simplicity for transistor M1, parallel to R0 2. So yeah, this is your effective impedance. Now we have output impedance and we have this topology, common source. So we can simply say, yeah, we can simply say this is your PMOS, drain is source is grounded, this is your input, and this is your effective impedance where we are taking the output. So yeah, this is your 1 upon GM1 parallel with R out 2 if CLM of M1 is not considered. So this structure is simply reduced to this resistance. This M1 is replaced by this particular 1 upon GM. And overall, if we are looking from this, so okay, this thing actually not parallel right now. Later, if I extract this resistance from M2, then it will become parallel. For now, this is only G1. Okay. For now, this is only GM1. So this is 1 upon GM1. So this M1 is replaced by its impedance, and this is your M2. So this R out is inside this M2. So if we draw its small signal, or no need to draw the small signal also, I can simply say because the input is applied at the M2 and output is taken from the drain of M2. So we can say that AV is nothing but minus GM2. So the effective R out is minus GM2 1 upon GM1 parallel with R0 2. So this R0 2 is the impedance when we are looking up. 1 upon GM is the GM1 is the impedance when we are looking down. So overall effective impedance is 1 upon GM1 parallel with 1 upon GM2. So here the consideration is, this is the complete expression for the gain. Here the consideration is that lambda 1 equal to 0 and lambda 2 where we are applying the input is not equal to 0. If the lambda 1 is also not equal to 0, if lambda 1 is not also equal to 0, then the effective impedance at the drain of M1, so we can say this for M1, this Rout 1, which is the effective impedance at the drain of M1 will be, I explained, 1 upon Gm plus 1 upon R01. So in that case, a complete gain expression will be minus Gm2 1 upon Gm1 plus 1 upon R01. This thing should be parallel with R02. But later on, I will explain here that R01 is very larger than 1 upon Gm. Similarly, this R02 is very larger than 1 upon Gm2, or can say Gm1 also. Okay. So from this perspective, you can see this GM1 is very greater than 1 upon R0. So this structure can be reduced minus GM2. If this GM1 is very greater than this 1 upon R02, this overall is again going to reduce to 1 upon GM1. So this is parallel to R02. So as I also said, this R02 is very greater than GM2. So this is also very greater than GM1. This is also very greater than 1 upon GM1. For this thing also, it is also very greater than 1 upon GM2. This is true because R0 are very large. So for the practical design, it will is equivalently. So this is a very high and this is a 1 upon GM is small. So effectively it is 1 upon GM1 because parallel of low and high is nothing but equal to low and high. So it will be your minus GM2 by GM1. So this is the simple expression for the gain calculation of this question. Okay. So I think this is clear. It is gain. So yeah, here I explain these two examples. So this is enough for this video. In next video, I'll explain the other example. Okay. Thank you.